Hello, my dear students, and welcome to a new chapter, or actually a new series of small chapters in this course. In the previous, let me say, half of this course, we have studied independently the main systems constructing a PV system or a photovoltaic or solar energy system, considering the PV modules itself, inverters, DC-DC converters, DC-AC inverters, net metering, grid connected, utility grid, and all these other issues. Starting from now, we are going to reflect this independently described blocks into one complete system through a series of case studies. In these case studies, we will have two main objectives. First is the technical perspective on a macroscopic or on a system view for a complete PV system. This PV system can be a DC or an AC. This PV system can be a grid connected, or it can be a standalone, or it can be a hybrid system with a backup diesel, for example, or any other renewable energy system. The second objective, which will come later on, which integrating the main economical aspects related to this system so that we can configure not only a technical case study, but what we can call a techno-economic case study for our PV systems. So let's now start considering one of these cases or case studies that we will use to learn some important aspects related to PV systems. This case study was already published in a conference in Dubai, I think 3-4 years ago, under the title Techno-Economic Feasibility Study for the Enrollment of Photovoltaic Solutions in Oil and Gas Industry. Okay, so let's consider the case. Here in oil and gas industries, one of the techniques used to make oil production is what's called a sucker rod pump. A sucker rod pump is a pump used to pick up or get the oil barrels from the below earth layers to the above earth layers. In order to perform these tasks, of course, we need some sort of an electrical energy to operate. Usually, some of these fields where we have oil and gas, we don't have a utility grid connected. Herein, we will be forced either to use diesel generators or to make some sort of a renewable energy, like a PV system. Of course, whenever we have a utility grid, then the possibility for a PV grid connected starts to appear. But let's consider first the first case, where we don't have a grid. We only have a PV system, a remote system with conventionally working with a diesel generator. So in this case, the first point to consider, my dear students, is what we call the load specs. What is the electrical specs of your load? And using these electrical specs, we will introduce the first step in sizing, which we call the load profile. So let's see what is our load specs and how we will consider these load specs in order to have or to implement what's called a load profile for our loads. As you can see from this table, my dear students, these are the specs for our sucker rod pump. We have a pump. It seems to be a 3-phase pump with 380 voltage. It has a rated current of 86 ampere. However, it does not work at a rated current. It has an operating current that differs with respect to the operation. So in the abstract, I mean, when the when the pump is lifting from down to up, it consumes 67 ampere. However, with the downstroke, when the stroke is going from up to down, it consumes only 30 ampere, where the power factor is 0.86. Okay, from these informations, my dear students, we can now calculate three different types of power. Let's see. So usually whenever I do sizing, I have this my Excel sheet where I'm going to do all my needed sizing process. So let me just close this annotation. Yeah, so we have a voltage. Sorry. Here, the voltage is 380. We have rated current of 86. And we have a power factor of 0.86. So the first we can do, my dear students, is to calculate the rated power, or we can consider it here as the worst case power. The worst case scenario power will be, let me say here, rated power. The worst case scenario power will be equals voltage time current time power factor. And don't forget, this is a three-phase voltage, so we have to multiply by √3, which is 1.77 approximately. So the unit here, or the power here, of course, the unit here is watt. So this is the power in watts. So we can write here watt. So you can calculate the same power in kilowatts. By simply divide that by thousands. So it's around 48.974 kilowatts. Okay, this is the worst case scenario power, because simply this power reflects the highest possible current to be drained from our pump. However, following the given information, we have an upstroke current of 67, and we have a downstroke current of 30 ampere. So you can here calculate the upstroke power and the downstroke power. The upstroke power simply equals the operating voltage time the upstroke current times the power factor times 1.77. And here, using this same formula, you can get the power in kilowatts, in kilowatt, as you can see. Okay, perfect. At the same time, you can calculate also what we can call the downstroke power as the voltage times the downstroke current times the power factor times 1.77. And similarly, you will get the power in kilowatts. So as you can see, my dear students, there is a huge fluctuation between both of the three scenarios. The overall power consumed in the worst case scenario, which is an hypothetical scenario here, because as you can see, we will not work at the rated condition, is around 50 kilowatts. Realistically, we consume 38.7 kilowatts during upstroke phase, and we are consuming a 17.35 kilowatts during the downstroke phase. So now we consider what's called the power. But as we already studied together during this course, whenever it's time to make sizing, you have to consider energy, not power. So as this power is considered some sort of a theoretical power, we are not going to consider this number. What we are going to consider simply, my dear students, is the real consumed power. So let's assume now this saccharide bomb is working 24/7. So simply speaking, all the time, the saccharide bomb is working. And let's assume a symmetric operation between downstroke and upstroke. So 50% of the time, the power is an upstroke power, and 50% of the time, the power is a downstroke power. So in other words, we can make something like that. If we consider here the time, and here the power, let's consider time in hours, starting with hour number 1, 2, 3, and so on. So these are the 24 hours. And on the other hand, we say that 50% of the time it's upstroke and 50% of downstroke. Of course, this is not, that means that it doesn't work a continuous 12 hours upstroke and a continuous 12-hour downstroke. Of course, this is a successive process, but for the simplicity of presentation, we will consider that 50% of the time, I mean from 1 to 12, sorry, here, equal the same power as here. And then we can copy this till 12. I'm sorry. I think I copied the format. I'm sorry. So I think. No, we have to make it like that, I think. So, sorry for that. So now this is the 12 values here, and the same, let's do it here. So this is equals the other 12 values, and let's fix the cells like that. And then we can get something like that. So we can now plot this data. So I think so insert here, and let's go to charts. Not this. Something like that, for example. Yes. So this is typically what we have. Well, so we call this, my dear students, as the annual load profile. This load profile presents the power consumption distribution among the 24 hours of the day. So herein, the x-axis represents the time in hours, the y-axis represents the power in kilowatt. So simply, the area under this curve represents the total energy consumed in kilowatt hour per day. And this is considered as our first step toward having a sizing process. So, as I just mentioned, this is a very descriptive way for modeling the pump, because realistically, pump is not working continuously 12 hours for a downstroke and continuously 12 hours for an upstroke. So to have a more realistic model, let's now skip the model of a pump for a while, and let's see another example with a living room, for example, with some lighting loads, air conditions, and whatever. And let's see how we can plot a load profile for such a living room with different electricity resources. So in the next part, my dear students, we are going to consider, of course, we will return back to this case study later on, which is a soccer road bump, still in the same lecture, but we will go just for a while to explore more about the load profile. And then we are going to consider the overall load profile, either on a daily, a monthly, and an annual load profile. So that's all for this small part, and let's see you in the next part, inshallah. Thank you very much.